Hi students, I'm going to teach you a bit on polarimetry. Now, most physical properties of enantiomers, such as melting point, boiling point, refractive index, etc., are identical. However, they differ in a property called optical activity, and in which a sample rotates the plane of polarization of a polarized light beam passing through. And this effect was first discovered in 1808 by E.L. Malus, who passed light through refractive glass surfaces. And in 1811, this was first observed in quartz by D.F. Arango, and you can see his face here in this slide. 4 years after the first discovery by E.L. Malus, J.B. Biot found that the extent of rotation of the light depends on the thickness of the quartz plates that he used. He also discovered that other compounds, such as sucrose solutions, were capable of rotating the light, and he attributed this optical activity to the certain features in the molecular structures, which is hence defined as asymmetry. And because of his research, he designed one of the first polaroscopes and formulated the basic quantitative laws of polarimetry. Now, in 1850, Villamy used polarimetry to study the reaction rate of hydrolysis of sucrose, and in 1874, Van Hoff, the guy from the Van Hoff equation, he proposed that a tetrahedral environment of the carbon atom could explain the phenomenon of optical activity. And today, polarimetry is used routinely in quality and process control in the pharmaceutical industry, fragrance, flavor, and essential oil industry, the food industry, and chemical industry. The optical purity of the product can be determined by measuring the specific rotation of the compounds, such as the amino acids, antibiotics, steroids, vitamins, lemon oil, various sugars, and polymers, and comparing them with the reference value, and if we know the specific rotation of the pure enantiomer. So how does it work? Normal monochromatic light contains light that processes oscillations of the electric field in all possible planes perpendicular to the direction of the propagation. And when light is passed through a polarizer, for instance, a Polaroid film, only light oscillating in one plane will leave the polarizer. And this linear polarized light can be described as a superposition of the two counter-rotating components. This is a bit more physics, so maybe you would like to slow down. And this linear polarized light can propagate with different velocities in an optically active medium. If one component interacts stronger with a chiral molecule, it will slow down and therefore arrive later at the observer. And the result is, to us, the plane of light appears to be rotated. So in a polarimeter, you see in this figure, the plane polarized light is introduced to a tube, which is typically 10 cm in length. It contains a solution with the substance to be measured. Now, if the substance is optically active, then the plane of the polarized light will not change in orientation, and the observer will read an angle of the alpha to be 0 degrees. If the compound of the polarimetry cell was optically active, the plane of the light would be rotated on its way through the tube. And this observed rotation is a result of the different components of the plane polarized light interacting differently with the chiral center. And in order to observe maximum brightness, the observer, who is the person or the instrument, person in the olden days, but right now we are all using machines, is all automated. So this observer will have to rotate the axis of the analyzer back, either clockwise or counterclockwise direction, depending on the nature of the compound. For clockwise direction, the rotation unit is in degrees, is defined as positive, and it's called dextrorotatory. It came from Latin word dexter, the show Dexter means right, you're right. And in contrast, the counterclockwise direction is defined as negative, and it's called levorotatory. And from Latin, levus means left. You know something? You can actually prove to somebody that left is equals to right. How? What's left is right when everything else is wrong. Okay? Unfortunately, there's no direction correlation between the configuration, the D and L, in these Rosanov denotations, and the R and S in the CIP nomenclature. Remember CIP? CM1121, organic chemistry, RS, right, of an optical center. So there's no direct correlations between these DL and RS of an enantiomer and the direction plus, minus, or positive, negative, in which way they rotate the plane polarized light. No link. This means that the R enantiomer can exhibit a positive or negative value for the optical rotation depending on the compound. And in some cases, the solvent has an impact on the magnitude and the sign as well. Like in acetic acid, it exhibits an optical rotation of alpha to be 3.9 degrees in water and 13.7 degrees in 2 molar sodium hydroxide. You see, different solvents, it just gives you a different value. And this is because the observer looks at the different species of the lactate that we're talking about here. So now the specific rotation alpha depends on few factors: the length of the tube, the wavelength in which it is used for the acquisitions, the concentration of the optically active compound, and to a certain degree, the temperature as well. However, take note, the temperature effect is very difficult to specify since it differs for every compound. For instance, the alpha value for the alpha pinene only slightly increase in the range from 0 degrees Celsius to 100 degrees Celsius, while it is almost cut into half for the beta pinene. And these two compounds only differ by the position of the alkene function. So in general, these following equations is used to calculate the specific optical rotation from experimental data. You should know what does a symbol mean, okay? Very important, don't just memorize the formula. Alpha stands for observed optical rotation. C, the concentration of the solution in grams per milliliter. And L, the length of the tube in decimeter, dm. Here are some examples for your learning. Suppose a student observe and obtain the following specific optical rotation from his measurement. This is what he has, okay? So how do you denote this? This means that the measurement was conducted at 25 degrees Celsius using the D line. What does the D stands for? It stands for deuterium, the isotope of hydrogen. Emits light of the sodium lamp, which is set as the wavelength to be 589.3 nanometers, and a sample containing 1.00 gram per ml of the compound in a 1 dm tube exhibiting an optical rotation of 3.5 degrees in clockwise direction. Note that the instrument used in CM3291 can provide the specific optical rotation, which already corrects the optical rotation of the cell dimension and the concentration. But the optical rotation data is raw. It's a raw data which does not include these corrections. So it is very important to pay attention which mode was used to acquire the data. Okay? Now, as mentioned earlier, polarimetry can be used to determine the optical purity and EE. EE stands for enantiomer excess, okay, of the enantiomer. So this is the equation, percentage optical purity. The numerator is the number of moles of one enantiomer subtracted from the number of moles of another enantiomer. And the denominator for this fraction is the sum of the two moles of the enantiomers, and after which you multiply by 100%, you get the percentage. And these are the other equations that you got to consider. Now, if you do not have the number of moles, so you can use the result from the polarimetry. This OP, not overpower, OP is also the ratio between the observed rotation over the rotation of the pure enantiomer. And how do you find the EE of a mixture? Now consider that you have a mixture of hypothetical enantiomers, positive A, negative A, and you got the number to be 75% and 25%. What you do is the EE is just the difference in these numbers. That's it. Example 2. The observed specific optical rotation of a compound alpha is to be 7 degrees, and the specific optical rotation of the pure enantiomer is 28 degrees, again positive. So the percentage optical purity will be 7 over 28 multiplied by 100% equals to 25%. It means that the sample contains 75% of the racemic form and an excess of 25% of the enantiomeric in question. Now these are the lab instruments that you see in the instrument lab opposite the synthesis lab. Okay, we'll be using this polarimeter manufactured by Bellingham and Stanley Limited, code number ADP440. And on the right side here, you see this is a 10 cm polarimetry cell. Of course, there are other lengths like 25 cm, so you need to really measure it, okay, and check before you do your calculations. And that's all for this lecture. For the usage of the polarimeter, you can check out the other video that I made for you. Good luck for your learning. Enjoy. Thank you.